Hello, our project is about classifying pose with 3 different classifiers. We have been inspired from the past Korean meme called Dancing with Be Noticed by the Teacher. Changing the situation to online meeting room, now is a game to perform a specific pose secretly in the meeting. The rule is simple. Each player randomly picks a pose among these 7 poses. During the meeting, they have to secretly perform their pose without getting caught. So our goal is defined as the problem of classifying detected human pose into 7 classes accurately. In order to classify pose of the video, coordinate was needed instead of pixels. Blaze pose common for converting video into coordinates. Blaze pose return 33 body key points which called landmark for the major body joint. Each landmark consists of x, y, z coordinates and visibility. We choose it because it was fast, lightweight, provide more landmark than others. And its detect plus tracking was stable through video frame. So our pipeline is video input, blaze pose inference, classifier, success count. Training dataset are images. For each pose we took around 150 images per class. Also we collected similar but not exact pose as negative examples. Because the dataset was small, we began with SVM, which is suitable for the small dataset, and then gradually expanded to MLP and GCN. First, support vector machine. SVM chose the boundary with the widest margin among the many that separate 2 classes. The closest point called support vectors define this boundary. A wider margin is more robust to noise, leading to better generalization to new data. Since SVM is a binary classifier, we use the 1 versus less stretch. 1 classifier per pose for a total of 7. The input is a 99-dimensional vector of x, y coordinates and visibility values normalized to reduce the effect of camera distance. We use an RBF kernel for complex boundaries and flat scaling for probabilities, recognizing a pose when the probabilities exceed 0.85. The test result achieved an accuracy of 0.88 and a macro F1 score of 0.89. However, the record for the elephant nose class was the lowest at 0.69. This was also seen in webcam testing, where elephant nose was often not recognized correctly or misclassified as energy wave. This is likely because both extend one arm forward, making the boundary between them less distinguishable. SVM is fundamentally linear, so when the data can't be split by a line or plane, we need a nonlinear classifier. On MLP's text layer, it's a linear transform followed by a nonlinear activation that bends the data space until the class separate easily. Unlike SVM, it learns nonlinear boundaries directly and finds useful features on its own. The MLP also used 1 versus less with 7 classifier with the same input and normalization. Each output passed through a sigmoid, and the highest probabilities pose is recognized if it exceeds 0.85. The test result achieved an accuracy of 0.86 and a macro F1 score of 0.88. However, since the MLP treats coordinate as a flattened vector, it can't capture the structural relationships between joints, lowering recall. As a result, player and elephant nodes were unreliable in the webcam test. Both SVM and MLP ignore the structure connecting wrist, elbow, and shoulder, and the solution to this is GCN. The third classifier was the Graph Convolutional Network or GCN. GCN tackles a different kind of data from the previous 2, social network, citation network, molecules, graphs with irregular structure and rich relational information. Since human pose is not independent points but connected body parts, we assume a graph structure would be more appropriate than SVM or MLP. We implemented it based on GCN paper by Kip and Welling. The core intuition is simple. You can understand a node by looking at its neighbor. A node's level is best predicted from its connected neighbors. This is similar to a CNN, which aggregates neighboring pixels on a regular grid, whereas a GCN aggregates neighbors on an irregular graph, where each node has a different number of neighbors. Mathematically, we sum the neighbor information at a self-loop so each node keeps its own features, and apply symmetric normalization so larger half nodes don't overwhelm smaller ones. Stacking layers leads further neighbors, but too many cause oversmoothing, so 2-3 layers are enough. We represented Blazeport's 33 landmark as nodes and the standard skeleton connection as bidirectional edges totaling 70, with the same normalization as before. The model has 2 GCN layers and 2 fully connected layers. Each GCN layer updates a node by gathering information from its neighbors. Then global mean pulling average all 33 nodes into a single vector, which pass through the fully connected layers to produce 7 outputs. A sigmoid converts these 2 probabilities, and a pose is recognized if the highest exceeds 0.85. The test result achieved an accuracy of 0.9665 and a macro F1 score of 0.9674, with most classes showing high precision and recall. It also recognized pose stably in real-time webcam testing. So, we adopted GCN as our final model to determine whether improving performance was possible. We tested our 2 hypotheses. The first was adding edge structure would improve performance since the key strength of GCN lies in the edge connecting the nodes. We added additional edges to the standard skeleton graph to reinforce the relationships between joints. The second was lowering the recognition threshold would allow the model to detect more poses, thereby improving the success rates. We tried lowering the threshold from 0.85 to 0.6 gradually. However, neither experiment produced a significant improvement compared to the original model before tuning. This suggests that the standard skeleton structure already provides sufficient information about the relationships between joints required for distinguished pose, meaning that additional edges contributed little new information. Likewise, since the GCN was already recognizing pose with sufficiently high confidence at the original threshold, lowering it did not substantially change the results. As a result of implementing and comparing the 3 classifiers, the GCN achieved the highest performance, since SVM and MLP process landmarks as simply arranged vectors. The spatial relationships between body parts are lost during training. In contrast, the GCN alleviates this by explicitly modeling the connections between joints as a graph. GCN was originally proposed for classification on graph-structured data, and follow-up studies such as spatio-temporal GCN have shown its effectiveness for skeleton-based pose recognition. In this project, we confirmed that graph-based modeling remains effective even with a limited dataset, and verified that choosing a model suited to structure characteristics of the problem can significantly improve performance.